Hello, everyone. Welcome to our talk. My name is Xiaoxin. This work is from Nanjing University, Alibaba Group, Zhejiang University, and Tsinghua University. Network functions such as NAT, private link, VPN, load balance plays an important role for the connections among tenants VPC, on-premise data center, internet users, and cloud service. Traditional hardware middle boxes just can't keep up with the ever-changing needs of cloud networks. They have long development cycles and lack of programmability. That's why the bare metal network functions are the game changer. They use x86 servers to build network functions because they are more flexible. But creating new bare metal clusters involves purchasing, construction, configuring, and verifying, and this can take months. Take shopping festivals, for instance. Traffic can increase by 100 or even 1,000 times. So network service providers must reserve a large number of bare metal servers for emergency events. The cost of maintaining such a large amount of infrastructure remains a significant challenge. To solve these problems, cloud service providers are looking for elastic solutions that can dynamically respond to changing business demands. A natural solution is using the ECS in cloud. This offers multiple benefits. It allows the network functions to scale using infinity computation resource, and pay-as-you-go price model can result in significant cost saving. High availability of ECS can minimize the impact on customers. Therefore, we aim to develop an elastic cloud-native network functions management platform over ECS, CyberStar. The platform must scale out to serve cloud-scaled tenants and scale up to handle millions of simultaneous connections for individual tenants. For instance, a tenant may require millions of simultaneous connections for NAT and generate 1 million new connections per second for load balance. Network function scalability is influenced not only by resource availability, but also by the complex internal execution logic and state consistency requirement. Therefore, the key to enhancing network function scalability is lying in decoupling network functions and effectively manage the states. This entails ensuring that each network functions instance is lightweight, independent, and capable of scaling on demand. Due to the variations in tenants distribution, we believe that resource sharing is an effective way to improve the utilization. To adjust large fluctuations, an effective auto-scaling mechanism can monitor the resource utilization. The auto-scaling can trigger a scaling out event when the system's capability are lower than the demand. And we can also trigger the scale in to reduce the idle resource. ECS has multiple factors such as performance, cost, and availability. To simplify the resource management, the straightforward method is applying a few types of prevalent and low configured ECS instance. This picture shows a typical network functions architecture. The network functions is deployed at the bare metal server. Some works like stateless network functions published in NSDI 17. It extracts the states and maintains the states in a centralized data store. Based on this design, the network functions process is stateless so that it can be scaled. However, there are have two problems. One is that the stateful component itself cannot scale out well under the cloud scale traffic. And the second is the remote access overhead is non-eligible, such as extra latency, CPU cycles, and higher bandwidth consumption. By investigating the architecture of various network functions, we observe that network functions execution can be separated into network function independent packet processing, network functions specific computation logic, and network functions specific state management. Due to the reliance on NF-specific logic execution on state, they should be put together for the faster state access. The state plane is NF-specific, performs service computation based on NF-specific state and logic, and generating flows that direct PP packet process on how to process packets. And the packet processing is a pipeline or match action unit. Each PP unit includes a parser match action table, which catch flows to instruct the PP unit on how to process the packet. When an incoming packet matches flow, the PP node processes the packet according to the action. If no matching flow is found, the packet is forwarded to the SC plane. As CyberStar scales, the connections between SC and PP plane becomes the bottleneck. It limits the scalability. For example, when the new SC node joins, this information should be notified to all PP nodes so that the PP instance can deliver the request correctly. We distribute the client's traffic evenly to the multiple PP nodes. When the new PP node joins, some existing flows may be reassigned to this new node, this triggering the repeat request to the SC plane. Therefore, we introduce a fabric master that manages the connections between the SC and the PP plane. When the new request arrived, the request will forward to any arbitrary fabric master node in the PP node. Then FM, the fabric master, that is FM, routes this request to the relevant SC node. After the decision-making process, both the packet and its flows is offloaded to the fabric master. After the fabric master do the replica of flows for incoming request, it will return the request and the flow back to the original PP node. Therefore, the CyberStar architecture is shown. Network functions orchestration is a service-oriented interface for users to describe the demand and realize cost-effective network functions auto-scaling through a schedule. And the network functions are divided into three planes: service computing, packet processing, and fabric master. Due to the stateless or PP node, we can further manage the pipeline of those units to fulfill service stream and complex network functions. Instances are added along the traffic path to extend the pipeline depths. Meanwhile, each stage of the pipeline is separately scaled out by adding new instances. Specifically, since the PP unit is network function independent, it can be shared by multiple network functions and tenants. For performance, we can deploy the hardware to accelerate the packet processing. We can get the lower latency and higher performance. Next is service computing. For reliability, node crashing leads to state loss. We should establish state replica to prevent state loss. For scalability, we should minimize the impact of sync-on-service computation. Multiple SC nodes makes up a reliability group as known as SCG, and the request pass through the reliability group to prevent the state loss. For scalability, we first do the state partition, taking source net as an example. By partitioning the set into like A, B, and C, D, we can distribute them into 2 SCGs. This allows each SCG to independently allocate address and port pairs for incoming request, ensuring efficient and independent operation. During the scaling-in event, the 2 sets also can be matched back together. Then we introduce the state sync during the scaling. An example of scaling out is as following. Scaling out is triggered when requests exceed the computation capacity of SCG1, then SCG2 joins. At the beginning of scaling out, FM sends a start signal to SCG1. Upon receiving the start signal, SCG1 partitions the state A into B and C, and then move the state from SCG1 to SCG2. After receiving the state B, SCG2 sends FIN to inform both SCG1 and FM that the state is ready. FM then dispatch new requests to SCG2, and SCG1 can delete the state B. In case of scaling in, when it determines that SCG1 needs to be released, the scaling in event is triggered. At the beginning of scaling in, FM sends a signal, ST, to the SCG1, instructing it to move the state from SCG1 to SCG2. After SCG2 merged D and F into G, it returns a FIN message to SCG1 and FM. Then SCG1 can be released. So Fabric Master decoupling the SC and the PP plane. It delivers the request to SC plane, so the scaling of SC is transparent to PP planes. And it caches flows for repeat requests. So the scaling of PP plane is transparent to SC plane. Furthermore, Fabric Master also improved the tenant access. For example, in the PP unit, each PP unit node has 2 ENI interface. One is from the VPC and one is from the cloud service. Traffic forwarding between the VPC ENI interface and the cloud service ENI interface. But ENI interface is a limited resource, which leads to scale issues for service and tenants access. So we introduce a fabric, full mesh fabric to manage the connection between the VPC ENI interface and the cloud service ENI interface. Traffic will go through the fabric, go through the fabric tunnel, and this fabric tunnel is managed by the Fabric Master. This picture shows that creating 100 million connections with the speed of 35,000 connections per second for 60 minutes. The network functions orchestrator monitor the resource utilization of each instance. When the new tenants request come in, it will select groups of instances to perform service computing and packet processing. When network functions orchestration finds out that one instance is overloaded, it sets up a new instance to scale. CyberStar has been deployed for over 4 years and is published available in our cloud. We introduced a new 3-plane architecture to address the scalability issues. We decompose the packet processing pipeline into network function-independent units, allowing the assembly of various network functions types. To improve the utilization, CyberStar introduced an auto-scaling approach to minimize the cost of cloud providers. Thanks for your attention.